So this is COMSC 142, and we've been talking about assembly language finally. We started with 32-bit Intel assembly, and then we did the same thing in 64-bit Intel assembly, and now we're going to do the same thing in ARM assembly. So I got my slides here. All right, and so, all right, this is, by the way, ARM version 8, which is 64-bit ARM. There is a 32-bit ARM, and it's used on small devices like older Raspberry Pis, and I imagine it's probably used on small Internet of Things devices like light bulbs and thermostats, although I'm not sure exactly which ones. But that's pretty common for the really small devices to use 32-bit processors just to save battery and make them smaller and cheaper. But anyway, we're going to only be using computers with 64-bit assembly in this course. 64-bit ARM. So, the assembly basics, of course. Here's the same program we've seen before. We have an adder 2 that will read an integer and add 2 to it. And then the main program will set x equal to 40 and pass it as an argument to adder 2, and then print the result, which is going to be 42. So the point of this is to show how subroutines are called and how arguments are passed into them. So we can get objdump, can dump out the code here as before, and you'll see here's the code that does it. Here is the preamble that subtracts 10 in hex, which is 16, from the stack pointer. Notice this strange structure where you have a verb and then 3 arguments. That is common in ARM assembly. So sub subtracts stuff, stores the register into memory, LDR loads loads memory into a register. And here's add, and here's return. So this is the start of it all. So these 3 instructions perform A plus 2. It stores the W0 register into memory at the location stack pointer plus 12. And then it loads the memory, W0 from that, which is kind of interesting. This seems pointless. You put it there and then you just pulled it back. But anyway, stores the register in memory, loads it from memory. This adds 2 to it in the register. All right. So the registers, there are 31 registers. Remember, in 8-bit Intel code, there were only about 8 registers, and that was not enough, so you always had to stick things on the stack. In 64-bit Intel, I think I might have said 16-bit, 32-bit Intel has only about 8 registers. 64-bit Intel has more, and 64-bit has 31 registers, which is really a lot. X0 through X30. PC is the program counter, the address of the next instruction to execute. SP is the stack pointer, the top of the stack, the location where you can store data if you want to make the stack grow bigger. LR is the link register, the return address from a function, and ZR always contains 0. So these are some special purpose registers. So there's a manual, and by the way, it's actually much more complicated. There are some more complicated detailed registers and a link to them all, but the simplified discussion of registers there is enough to do what we're doing in this class. So there's also advanced register notation. You may remember the same thing was true of Intel. You could refer to the whole register as X0, or you can refer to the lower 32 bits as W0. And that's, all right. And by the way, when you use W0, the rest of it is all set to 0. So here's the structure of an instruction. You have the opcode and then 3 parameters. D is the destination, and O1 and O2 are the operands. So here I'm going to add put the answer in W0 and take W0 and add 2 to it. So you put W0 in here twice, whereas you wouldn't put it there twice in Intel. That's just the way ARM syntax is. So add into W0, W0 plus 2. Right, a constant is preceded by a pound. Registers are written like W0 or perhaps the stack pointer if you're going to refer to one of those special registers. Memory locations are in brackets, just like before. If you have 2 values here, you add them together. Take SP and add 12. And I think this 12 is in base 10 because it doesn't have 0x. And that's a pointer dereference. This will be stack pointer plus 12. So here you have some data. If I have 804, 808, 80C, and 810 containing these values, and I have the registers containing these values, X0 is a pointer to that address location. The others are just smaller numbers. So X0 itself contains 804A. Bracket X0 is the pointer to this memory address, which contains CA. Pound 804 is an immediate constant. It just means that address, that number, 804 in hex. X0 pound 8 is going to be take X0 and add 8 to it and then interpret it as a memory address. So that'll be taking 80A, 804, and adding 8 to it, turning it into 80C, which points to 12. X0, X1 is legal. That's going to take two registers and add them together to create an address. If you take X0, which is 804, you add X1, which is C, you get 810. That's going to be 1E. Yep. Then you have X0, W3, and SXTW. This is called sign extend memory. So, let's see, W3 contains a 4. So sign extend W3, X0 is 804, and I don't quite understand this one. Sorry, I forget what this sign extend memory is. And there's scaled memory. All right, I'm not going to worry about them. I'm not sure I haven't used any of them in my coding either. I've forgotten what those crazy things are. Here we are. It's going to tell me. Sign extend extends the 32-bit W3 to 64 bits. Oh, I see. It's because you're adding an X to a W instead of adding an X to an X. An X is 64-bit and the other X is 64-bit. If you want to add a 32-bit, then you extend it. And if you sign extend it, you take the leftmost bit and duplicate it in all the high 32 bits. So if it's a negative number, it stays negative. And if it's a positive number, it stays positive. Okay, so it's just a way to turn it into 64 bits. This is interesting. I don't remember having to do that in Intel, but I'm not aware of Intel instructions that add 8 bits to a 32-bit register. This is kind of a screwy thing to do. Okay, and this is going to do left shift left pound 2, so that's going to take the X2 and shift it left by 2, which is going to multiply it by 4. We talked about this last time. Every time you shift all the bits left by 1, you double the number. And here's one that's going to sign extend and scaled memory. What does the pound one? Also shift left by 1, apparently. That's interesting. Okay, so that's going to double it. Anyway, these are pretty exotic things. I wouldn't do them in writing code manually. I would just use 2 instructions. These are things a compiler might generate. But getting that fancy just confuses me. All right. All right, you can't, now here's one thing that's real important in ARM code. In Intel code, you would add to a location in memory, but you can't do that in ARM code. You can only work on registers. So the process is always take the data from memory, put it in registers, work on it in the registers, then write it back to memory. So it takes more total instructions to do a job than it does in Intel, and that is by design. Intel was a CISC, Complex Instruction Set computer, where you have many, many instructions, like 10,000, and they're all minor variations on each other. Like you have add immediate value to memory, add immediate value to register, add register to register, add register to memory, and so on. In ARM, you have a reduced instruction set. You don't bother with all those versions. You can just add register to register. That's it. You can subtract register to register, and so on. And so you have to move. It takes more steps. And the idea is it would be more efficient to have a smaller instruction set, more optimized. So even though you have to execute more instructions to get the job done, you'll lose less power. And that is absolutely true. ARM processors run faster and use less power. And this has been predicted for about 10 years that ARM is going to replace Intel everywhere because batteries last longer, you need less cooling and less power on your data centers and so on. And that's very slowly happening. Although, as you know, the Mac moved to ARM when it switched to the M1 series, which is now up to the M5, so that's several years now. I have been told that you can now buy Windows on ARM PCs, on ARM hardware, although I've never seen one. My virtual machine is ARM because it's running on a Mac, M1, but and I haven't heard of very many data center servers running on ARM yet. And these things will be slow because of all your code has to be rewritten. So all your applications won't run on ARM very well right now. They run through a translation library. But as time goes on, people are writing more and more of their programs to run natively on ARM. So probably over the next 5 to 10 years, you're going to see everything move to ARM because the power savings and time savings and cooling savings make it more logical to run everything on ARM. There's just going to be a transition period as we move away from Intel, unless, maybe Intel will surprise us and actually write a better processor, but Intel is pretty much swirling down the drain. The last 2 generations of Intel processors have had serious flaws that created big scandals, and they don't seem to be a successful company anymore. It looks like Intel is just going to pretty much go extinct. AMD may live for a while, but ARM seems to be the future. ARM is, however, by the way, proprietary. You have to pay a license fee to use it. If you don't want to do that, you do what China is doing and use RISC-V. RISC-V is the open source imitation of ARM. It's essentially identical, but you don't have to pay any license to use it, and China is now manufacturing hardware that runs it, and you can get a RISC-V computer, although they're pretty much small and not very powerful ones yet. They're coming, hardware that runs RISC-V. Anyway, so in America, the most important processors are Intel, which is equal to AMD, and ARM. And ARM is the future, and Intel is the past. All right, so and like I said, a destination of every operation has to be a register. Like I'm saying, you can't write directly to memory. All right. Well, you can write a register to memory, but you can't do anything other than store and write to it. So here's common instructions. Load the value in memory into a register. So here's the destination here. Notice, by the way, the first argument is not always the destination, just to be as confusing as possible. Store register writes the S source into the address. So I found this very annoying. Remember in Intel, I would talk about the difference between AT&T and Intel syntax, or one of them puts the destination on the left and the other puts the destination on the right. Well, ARM puts the destination on the left for a load, but the destination on the right for a store. So a little bit screwy. You have to get used to that. All right, this will copy the value of source into destination. This will combine these two values and put them in destination, O being, I guess, a marker for general argument. And this will subtract these, 1 minus O2, and put it in destination. All right, so this sequence of instructions: store the stack pointer plus 12, the value at that address, into W0, then take W0 and write it back to the stack pointer 12, which seems unnecessary to me, and then add W0 plus 2 and put it here. Store the value in W0. Oh, that's because I'm reading it wrong. Let me say it again. Finally, it makes sense. The data came in W0, you write it on the stack. Then you load it from the stack, then you add 2. The part that confuses me is you don't need this part, but I think it's generated by a compiler that's just going through a general process. Put all the data on the stack, then when you want something, load it from the stack. This LDR is clearly not necessary. It's already in there. So I would think a more optimized compiler would skip that part. Anyway, that adds 2 to the argument. So if you compile that without optimization and view the assembly code, then you'll see the code we saw here. That's right. And if you turn on the optimization, minus O1, good, there you go. Now it does something much better. It takes what's in the W0, adds 2 to it, and puts it in W0. You never needed to put anything on the stack at all to get the job done. So this is optimized code. All right, that makes sense. All right, so you can load and store a pair. This is going to take destination 1 and destination 2. It's going to load X0, and the next one's going to take the next 8 bytes and put them there. So 64 bits here and 64 bits there. So this moves 128 bits in one instruction. Here it's going to offset it by 10 and then put the 128 bits in these 2 locations and so on. So you can move 128 bits at a time. And that's because of the P here, load pair, a pair of 64-bit words. All right, so let's try this adder 2. I think I've got it set to go here. So here's an SSH shell into my virtual machine. And if I do uname minus A, I can see that I do in fact have ARM64 processing here, okay? And let's see if I have this program here. I don't, I'm going to get it. So let's get adder 2. All right. All right. And then GCC minus O adder 2, adder2.c. Okay, so if I do a file of adder 2, it is this ELF 64-bit executable ARM. AArch64, 64-bit ARM. So that's, and if I look at the code, it's the same code we talked about where you have a function called adder2 that adds 2 to the argument. I put 40 in X and pass it in as an argument and then print it out. So let's break into it with the debugger. GDB minus Q adder2. We don't have GDB. Well, that's rude. Okay, let's do sudo apt install. I think GDB will do it. Oh no, that's the wrong password. All right, there we go. All right. There we are. All right, now we're in here. Now we can get rid of the stupid colors. And then break at the start of adder2 and run just to get to where it starts. All right. And then disassemble adder2. And here you see this code we've talked about before. This sets aside room on the stack, and this copies the input, which comes in W0, onto the stack. This loads it off the stack. This adds 2 to it, and then this restores the stack and returns. So this is the preamble, creating a stack frame for this subroutine, and this is the part at the end, the epilogue. Yeah.
And if you optimize it, then it wouldn't show that second load.
Exactly. If you optimize it, both of these will vanish because both of those are unnecessary. The data came in W0 and we're sending it out in W0, so we really didn't need to put it on the stack. Exactly. Good. So this is the unoptimized code, and so we can print the stack pointer. All right, and there's the address ending in F300, and we can examine it with x/12x, and it's $SP minus 30 to see the region I want to see. Right, 30 in hex. All right, so here's the data, and you see in came 40. Oh, I've just entered the function, though, so I won't see the 40 yet. In fact, I should be able to print W0, which would be $W0. There, here comes in the 40, and it's showing it to me in base 10. So there, so when I execute, the first command is going to make room on the stack. The next one will copy that 40 into the, yeah, there's the prologue and the epilogue. We talked about that. All right. And so if I do the next 4 instructions, which will be creating the stack frame, storing the parameter 40 on the stack frame, loading it back down, and adding 2. So let's do next die 4. And we'll disassemble adder2 just to see where we are. All right, so now we're down here. And now if we print the stack pointer, it should have changed. The stack pointer used to be F300. Now it's F2F0. We subtracted 10 from it to make room to store local variables. And if we examine the area near the stack here, then we're going to see the 28 somewhere here, I think, although I'm not seeing it. The 28 is stored in the nuclear. It should be on the right. And I don't know why I don't see it. That's a little disturbing. This should have stored it in stack pointer plus 12. Oh, I think I need to look a little further. Let's try looking further, like 16. Yeah, there it is. It's down there. Don't know what happened before, but there it is. It's available. It's on the stack. All right. And then we can print the link register /x link register. All right, that's going to be our return address. AAA stuff is going to go back to our code that we came from. And you can see here's code, AAA. That's where the code is. And this is more code. Off the end of this is going to be the main function. And you can see it by disassemble. Is it main? Yep. So here you see, here's the code that called adder2. and here's the code after it, 784, and that's what's in the link register. That's the return pointer of where to go when we return. All right. Notice the return pointer is not on the stack, so a buffer overflow attack is going to be less successful here. All right, so then you got arithmetic instructions. You can add. It's going to add these two things and put them in a destination. Subtract will subtract them and put them in a destination. Negate will negate this number and put it there. You can add with carry, which is going to add the carry bit, which might be set from a previous instruction, which is what you do for high precision arithmetic. And you can do multiply and divide as before. All right. And you can do bit shifts, which we talked about. So every time you shift to the left, you double a number, and there's a logical and an arithmetic shift. I think they're the same for the left, but on the right, yeah, logical arithmetic are the same for the left. The issue is when you shift to the right, do you feed in zeros from the left, or do you copy the leftmost bit from the left? If you copy the leftmost bit, you preserve the sign. That's arithmetic. If you feed in zeros, that's a logical shift to the right. So this makes more sense for things like encryption, where you're deliberately just shifting the bits around. This is what you would do if you actually, these are integers, and you want to maintain the integrity of your numbers. All right, and then there's rotate, which is where you shift to the left and then wrap that bit around and feed it in on the right. So it's, again, a screwy operation. There's no simple mathematical meaning that you might do as part of something like encryption. All right, and so here's some examples of doing it. This is an ampersand, a logical and, bitwise and, bitwise or, exclusive or. This is a negate, and you can have a combination of them here, so various binary operations. All right, and I see no comments in the Twitch. Let's try a Kahoot. Should have them ready to go, and that would be 9A right here. There we go. All right. All right, we have 8 online and 3 in the room, so we should get a few here. All right, so which instruction will store data from a register into memory? Is this one? It's a store, and the brackets are what makes this a memory address. All right, how long are ARM V8 instructions in machine code? Wow, I didn't notice this going by in the slides. It's an interesting factor. All right, this is, they're 32 bits, strangely enough, which means, by the way, that you don't have enough room to store an immediate 64-bit address. So strange things happen when you try to address certain memory locations. And it's always the same for every instruction, which is a big change from Intel. Intel had a different length for each instruction. ARM instructions are always 32 bits long. A strange feature of ARM. All right, And what does the ZR register contain? It always contains 0. I don't know why it exists, but there it is. All right. Go back to here. Okay, so conditional control and loops are available as before. So you can do a compare of two numbers or a test of two numbers. And in both cases, it will change the flags. So if these numbers are equal, you'll get a 0. So then you have the branch instructions. This is an unconditional branch. Go to this address. Here's a branch if the last comparison operation ended in a less than or equal. And you have many of these. Branch PC equals A, branch address L. Okay, that'll move to that address. This will move to A, right, okay. This will move to that address. This will move to this value, which I think is a register. If R is equal to 0, it will branch, a conditional branch on 0, a conditional branch on non-0, and here's a condition, branch.c to the address. It'll branch on this condition, and the condition can have various values. Those like equal, not equal, minus, if non-negative, and so on. So you have the same stuff you've seen before. Branch if something is positive, if it's negative, if it's 0, if it's not 0, all the usual stuff. So an if statement. We talked, here's an if x is greater than y, then put y here, otherwise put x here, then return. And so here's how it looks like in assembly. Here's the preamble, setting up the stack pointer. Here you're storing the incoming parameters, W0 and W1, on the stack, and here you're loading them from the stack. So now W1 and W0 contain the values. So again, those 4 instructions could be removed by compiler optimization. But anyway, then you compare them. W1 and W0 are these two values. So if it's less than or equal, then you go down to plus 40, which will be here, and load the register from here. Otherwise, you load the register from the other value and store it, and then you branch to plus 48. So this is just the same structure we saw in the other forms of assembly. You have a comparison, you have a conditional branch, and then you have an unconditional branch, because you have to execute this code in one case, and you have to skip over that code to not execute the other code. So that's the assembly language structure for if-else. All right, and so here you go. That's just explaining what I did explain there. And here's the conditional select instruction. A conditional select, this is another way to do it. With a conditional select, you'd compare them and then do a conditional select. So if W0 is less than or equal to W1, here's the condition, then put that in W0. So I guess these are the two. So this is a much simpler way to do it. Like I say, these conditional select are smaller, probably faster assembly code, but a little harder to read. So, all right, and we saw that I think in Intel too. And then there's loops. We talked about these before. You can have a while loop, or you can have a for loop that does the same thing. Here you start I at 1, you have a while loop, which adds it until I gets up to n, n being parameter, and then stops. Here you have a for loop that goes from 1 to n, adding until. They both accomplish the same thing, and therefore they both are exactly the same in assembly code. The only difference here is style for the human to understand the code they're writing in C. Here's the code that does it. Prepare the stack, store the variables n, and put a 0 there. Assign 1 to W0. So then you're going to have an unconditional jump to go down to plus 52. And that's interesting. You have I and N here. Oh, these are comments. That's why. Okay. So now you're going to load the value off the stack, which is I, into W1. And W0 is going to be n, so you can compare them to see if I is greater than n, if you're at the end of the loop. And if you're not at the end of the loop, then you jump up to plus 24, where you add 1 to the total here. And so you add 1 to the total, and you keep going until you're no longer in the loop, and then you go down. And so this is exactly the same kind of structure we saw in Intel code. All right, and then functions we've talked about. So you branch, BL will branch into a subroutine, and this will set the PC to this address, yeah. And you can also have a register for that address, is all this, and here's how you return. So that's how you branch. That's the equivalent of call in Intel, and this is return, which is the same in Intel. And as we saw before, and the same thing's true of 64-bit Intel, the parameters are passed in the registers, not on the stack, typically. You have enough room for 8 parameters in the registers, and that's usually enough. Although if you have more, it'll end up on the call stack. So that's why we saw before that the data you need was already in X0 and X1. You didn't really need to copy it to a local variable and copy it back for a lot of these simple functions here. All right, so here's adder, and we've seen this one before where you go up here, don't have any incoming parameter, but you have a local variable which goes on the stack, and remnant causes that value to be remembered and read here, and that's the game here. We've seen this before. I don't think I'll do it live. It's a little too confusing. But the point is here, here's the code for the assign function, which prepares a stack frame, moves the move. That's interesting. I was not aware of a move command. I also saw a store register and load register. But this puts a 40 in there, okay? That's how you put an immediate value in W0. Then you store it on the stack and load it from the stack, add, and then return. So this puts a value on the stack, which was intended to be a local variable, forgotten when you leave this routine, but it's remembered on the stack. And so when you go back with a later function, in the assign function, this 28 is sitting there as if it had been passed in as a parameter and is used by that function. And this is one of the common flaws of C, and for that matter, assembler. When you call a subroutine, it looks on the stack to find the parameters, and it doesn't know whether you actually put the right value there. So it will just take whatever value it finds there. And when we do the print string vulnerability, you'll see how to exploit that and take over a machine with that flaw. All right, so you end up with a output of 42, even though you didn't actually pass the parameter and it was just left over on the stack as data, which we saw in the previous Intel versions as well. And of course, there's recursion. You can write code that calls itself, so it runs with value of n, and then calls itself at n-1, and so on until it gets down to 0. So you end up with many copies of the program in memory, many stack frames. As it runs, it recurs itself n times, and then it returns from each of those n times, freeing up that stack memory, although leaving the remnants of it in the stack, because the stack is never cleared, not until you write on top of it. All right, and you have arrays, just like before. You can define an array with 10, and then you have, so x1 contains the address of the array. So here we go, x equals array, and x equals array 0 will load the data at x0. So the array itself refers to the pointer to the start of the array. This is the first element. This is array sub I, so it's going to be x2 is I, and left shift left will multiply it by 4 by shifting it left by 2. So this will take the address x1 and add 4 times the value of x2, which is an integral counting how many 4-byte integers you want to move through. Here's array 3, that's going to be shifting by 12, 3 times 4. Here's the address itself, x plus 3, and here's array plus 5, that's going to be 20, 5 times 4. So that's the usual stuff. So an array with 10 elements, you have elements like this, and here's where they're stored every 4 bytes, 4, 8, 12, 16, and so on. We're not going to bother with matrices, but we can look at structures where you have things like a 64-letter string and then a couple of integers and a float, so you'll just be lined up in memory. 64 integers, 64 characters, 1 byte each, then an age, which is 4 bytes, and another integer is 4 bytes, and then a floating point variable, whatever size that is. I'm not sure if it's 4 or 8 by default. And that's a student. So you initialize a student by referring to these elements, and that's just storing to various offsets here. These offsets point to the correct number of bytes in, just like it did before. All right, and again, you should have the same issue of data alignment. So if you had only a 63-byte field for the name, then you'd have a padding byte here because your 4-byte data starts on a 4-byte boundary. You don't just start randomly. All right. Then you got buffer overflows, and let's give this one a try. Let me get this, because this is interesting. The buffer overflow is different in ARM. So let me run this here. There we are. Let's get out of the assembler, download the code. Okay, and check to see if I already have it. I think I don't on this machine. Okay, it's going to be secret. I don't have it. Good. So we run packet with tar. And then we go into the directory. All right. And look in here. Here's an executable. Okay. So we run secret. It asks me for a number, and when I put in 1, it tells me I'm wrong. But if I put in a long string, then I get a bus error, which I think is the equivalent of a buffer overflow. So user input can be longer than the buffer size is only 12, but the scanf will read as much data as the user puts in, which might be more than 12, and that's why you get a buffer overflow. So if you put it in the, bus error is what you get. And so if you run it in the debugger, you can figure out how to control it. So gdb minus q secret, and get rid of the colors, and run, and then feed in this value. All right. And so it crashes, and here's the instruction pointer, which is 4949 and 4A4A. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. It's some of the I's and J's are what ended up in the instruction pointer. And if I do info registers, I'll see them here, and here's the program counter. And there you see it, the 4949 and 4A4A. So it was the last 4 I's and the first 3 J's are what ended up in the instruction pointer. So now that I know how to control it, I can disassemble endgame, which is the address I want to get to. Just get this, it's A's, a lot of A's and 0 ADC. And I can make a disable address space layout randomization as before, so it doesn't keep moving around. And here's the Python code that will do it. I put in everything up to the H's, and then I put in the desired address backwards. A lot of A's and 8EC, and then when you run that, you'll get the winning message. So we've done this before. That's how the buffer overflow works. All right. So, all right. So your address space layout randomization is one defense we talked about before. I had to turn it off to do that attack. So this is what randomizes things in memory so you cannot find out what address to jump to. Stack canaries put a flag at the end of each stack frame to notice if you're running off the end of the stack frame. And data execution prevention removes execute permission from areas that are writable. Now, I should mention, for completeness, I mentioned before this buffer overflow would not work because the return pointer is not on the stack. The reason it worked is that you put in a very long string here, and what you did was overflow from the subroutine into the main routine and overflow that return pointer. So it's actually a little more complicated inside, but the end result is pretty much the same. If you put in a long enough injection, you will hit a pointer that does end up in the program counter eventually. All right. And so as before, you can use safer C functions. Instead of using getF, you use fgetS. Instead of using scanf with %s, you put a number here. It is the programmer does have the capacity to limit how many bytes you read and make sure it's not too many, but it turns out in practice that expecting programmers to always remember that is not a good move, and they often forget, and that's why a lot of people are just fed up with this, where they want to quit using C entirely and just use Rust, which is as fast as C, but intrinsically avoids most of these problems. but there's a huge legacy code C and a huge bunch of developers that love C and defend it vigorously and say, you guys just need to get over being stupid and use C correctly and it'll be fine. Although I think 30 years of experience show that it's not fine in practice. Anyway, that's your safer source code that wouldn't have this problem because you only read 12 bytes, so it won't overflow. All right, let's try the last Kahoot here. I'm pretty much in favor of Rust because I think developers have enough to worry about. Expecting them to remember all these security rules on top of their other problems is just not practical. But the battle is raging. Small parts of Windows and Linux are the kernels are being written in Rust, and the communities are battling like crazy over this. The C people are saying, get this Rust out of here, and the Rust people are saying, get this C out of here, and it is not resolved yet. All right, which instruction will jump? Only if the previous instruction resulted in 0. All right, branch equals. That's what it means. Branch if the last thing resulted in something equal to 0. All right. All right, which one is a normal function call? Aha, pretty good. See, this is an unconditional branch. That's a go-to, go there but never return. This is branch with a link register, remembering how to come back. That's a normal function call. Branch with a link. Go down there and remember how to come back. And these are just conditional branches. So that's the equivalent of call in Intel code, BL. All right. All right, and what's the security measure that marks memory regions not executable? That's DEP, Data Execution Prevention. Your data regions that you can write to cannot be executed. All right. All right, good. So that's the end of the lecture part. Let me stop this recording.